Hello, in this video I'm going to be talking about paired tests, in particular for the two non-parametric tests that we've just covered, which is the sign test and the Wilcoxon signed rank test. And we're going to be working with paired data for those two tests. The techniques are going to be essentially the same as what we've done before. The distributional assumptions are slightly different, which I'll talk about now. Essentially, the two, for both the sign test and the Wilcoxon signed rank test, we need to have the distributions of the two pairs to be the same. I probably ought to show you the first example to show that we can see what we mean by paired data. So there's an example of paired data, which we'll do this in an example in a moment. You know, you've got two sets of golf players, and no, you've got one set of golf players, and they're playing in good and bad conditions, and the data occurs naturally in pairs. And when we can consider things in pairs, then we are better off doing that. If we were to just do kind of the other test to look at the differences, the other kind of things we might do without considering the pairs, we would definitely lose information that might mean that we miss something. And similarly, I've got another example here: reaction times. A little bit of perhaps a bit of a dodgy question. Reaction times taken from an old textbook where it was probably considered okay to talk about people drinking beer in a college textbook example. Drink responsibly, folks, if you're over 18. Anyway, so what we have is I was talking about the distributional assumptions. They need to be the same shape, but they can differ. For example, they can differ in position. Of course, that's essentially what we're testing. Whether the medians are different, for example, so they could be different positions like that. That's kind of what we're testing, because obviously the location will be different, and we're using the median as the location here. So location of the distributions can be different, and that's what a hypothesis test is doing. But the general shape is the same, which often you might think is a fairly reasonable assumption, but yeah, so that's an assumption we make, and that is for both tests. So you might recall before the sign test, when we were talking about just unpaired data, just one set, that this one didn't make any assumptions, whereas this one relied on symmetry. Well, whereas both of them for the paired set rely on this kind of same shape of distribution. If you think about it, if we were to look at the difference between these two, the difference between sets of observations from these two, then that would be symmetrical. So in other words, the kind of test statistic, we're going to look at the difference between the two. And that distribution, because the shape of the distribution is the same, the shape of the difference between the two distributions will be symmetrical. So if we have that, if that assumption holds that each of these sets is of the same shape distribution, then the distribution of the differences will be symmetrical. So that means that the Wilcoxon signed rank test can be used, because that's the thing we're going to do the test on. But we can use the sign test as well. Now, I have said that the Wilcoxon signed rank test is, if you can assume that symmetry, is normally the best, most powerful test to do rather than the sign test. And therefore, because both of these work, if the distribution of the original data is a similar shape, why would you ever do the sign test? Because this is more powerful in these circumstances, and that's a good question. There are instances where signed data can be used for categorical data, and for those you are my students, I might actually set the homework on that, where the sign test can be used for categorical data, and therefore that would be the way to go. So I'm including it here, even though the Wilcoxon is probably for paired data a better way to go in most instances. Okay. Before I get on with the question, you probably wanted me to get on with the question, um, is I would also say, just to go around the point home, these are non-parametric tests. Paired data paired data doesn't have anything directly to do with parametric tests or not. It's just that those of us covering OCRA further maths will not have seen kind of examples of paired data and hypothesis tests on, and this will be the first time you've seen it. But a very, very common technique for examining paired data like this with small samples would be the student t-test, and that is a parametric test, and it would assume that they are normally distributed. Okay, which in this case, in the case of golf scores, well, can we assume they're normally distributed? Is it reasonable? So on, again, using a non-parametric test is the more cautious approach. Okay, let's get on with the question. As I said, we're looking at whether there's evidence for a increase higher scores in bad weather. For those of you who don't know golf, obviously the number that having a higher score is a bad thing because it's taken more shots to finish the round. So, are you actually playing worse? In other words, in bad weather, and does the data here support that? And we're going to base it around the median. Let's just set this thing up then. So solution, and I'll copy in the table here. So let D be the difference in scores let's leave it like that for the moment. So D is a difference in scores. We are going to, here we've got a difference of +2. Here we've got a difference of +6. Here we've got a difference of 2. Here we've got a difference of 1. Here we've got a difference of 4. Here we've got a difference of 2. Here we've got a difference of -3. Here we've got a difference of 5. Here we've got a difference of 3. Here we've got a difference of 2. So let's let X be number of players with higher score. You could make it lower, but I'm just doing higher just to be consistent with the hypothesis, with higher score in bad weather. So where X is therefore presumed to be, under the null hypothesis, which I'll write in a moment, binomial 10, because we've got 10 golfers, and 0.5, presuming that there's no difference between, basically we should on average have an even distribution of positive and negatives. So H0 is MD equals 0, so the median of difference is of population of golfers, not just these 10, obviously this sample of 10 of the whole lot of professional golfers, that the median of differences in score, so MD is median in differences scores in good and bad weather. So in our on average, there isn't a difference. Right, and then the alternative hypothesis is that it's higher. So we have MD is greater than 0. Okay, and we've got 9 out of 10 being greater than 0. So it's one-tailed, so let's find the probability that X is 9 or something even more unlikely than 9. That's 9 or 10 basically, greater than or equal to 9. I'm going to, because of the way the calculator works, I'm going to use symmetry here. Because we're presuming 0.5, that's going to be exactly the same as probability x is less than or equal to 1. So we could have used the word lower in our definition of x, and we would have got directly to that, and we would have reached the same calculation essentially. So we're working out this on our calculator. So go to menu 7 on the calculator, and we want binomial CD, press 1, then press variable, because I'm not interested in a list here. I must have done this one before because the number's already there. 1, 10, and 0.5. So 0.0107. 0.0107, which is less than, because remember it's a 5% significance level we're looking for. So that means we do reject H0. There is sufficient evidence the median score of professional golfers is higher in bad weather. Okay, so that's how the sign test works for paired data. Let's say how often you'd be asked to do this is questionable, because in most instances the Wilcoxon rank test, paired test will actually do a better job. But yeah, so let's do an example of that. So here's an example about two groups of young adults who are doing this thing on reaction times to test the effect of a pint of beer, or a small amount of alcohol, relatively small amount of alcohol, on their reaction times, and to see if there is evidence here to suggest that that there's an increase in their reaction times. Okay, again it's one-tailed. So let's do this test. Okay, so again we're looking at D, the difference between the reaction times before and after drinking a pint of beer. So let's write those in. Positive if it's greater than, so that's 0.04 there. Here we've got minus 0.01. Here we've got 0.02. Here we've got 0.06. And so on. Taking care with that and making sure that the signs are correct and all that. So now, just as before, we're going to rank, but it's kind of, we're going to take the modulus of the rank, if you like, right? So we are ignoring the negatives. Now some people put another row here of taking the negatives out, but I don't see that that should be necessary. Just pretend the negative is not there when you're ranking them. So the lowest magnitude is 0.01, so that's 1. The next is 0.02. And then there's they've made it a little bit nice for us here. No, 0.03, 0.04, 0.05. It won't always go up as nicely as it does here, but then 6, 7, 8, 9, 10. I suppose it's been quite nice in getting the order right there. Just take out the negatives and then rank them. You just look at the the magnitudes and rank them in order like that. And then this is the key thing, the thing called the signed rank. So that's basically the rank, but reflecting back on whether it was a positive or negative difference to get the signed rank. So the signed rank there is 4, gives you a positive difference. This one's -1, this one's 2, this one's 6, this one's got a negative difference, that's -5. That's 7, 9, 8, -3, and this one here is 10. So that's a signed rank. Okay, I just realised I've forgotten to write the hypothesis. The most important thing in a hypothesis test is to set it up properly, and we normally do that towards the beginning or at the beginning. If this happens to you in the exam, you're okay to write it now, but I'm going to cheat and make a little gap for myself and write it above. So a null hypothesis is that MD equals to 0, where MD is the median of D, and we've defined what D is before, so it's fine. And then we've got H1, and it's talked about it increasing again, so MD is greater than 0 is our alternative hypothesis. Okay, so got away with that one. Okay, I say it wouldn't matter as far as the exam goes if you wrote it below, but if you can find a gap up, that's better to write it before doing all the analysis, because that's basically, in the world of applied statistics, that's what we do. We write the null hypothesis, then we analyse. So, right, so here we go. Remember that this process is kind of certainly from this point described in the formula sheet for OCR. W plus is the sum of the positive ranks, so that's 4 plus 2 plus 6 plus 7 plus 9 plus 8 plus 10, and that is pretty big, 46. And W minus equals to the sum of the negative ones but modulated, so that's -1 plus -5, let's just write -5, -3, which is equal to 9, and we take the t value as the smallest, which is equal to 9. Incidentally, because of the nature of the hypothesis going greater than 0, we would always be looking at the W minus here, unless the hypothesis is ridiculous. So here we would probably be looking at W minus because of the nature of the hypothesis, but it shouldn't make any difference anyway. So if you just get used to taking the smallest, it will always be correct. Okay, but it will also be, in this case, it will be W minus, and if the inequality was the other way around, it would be W plus, and if it was two-tailed, it could be one or the other. So, but yeah, just take the smallest and you'll be fine. Right, so now we're going to look at what the critical value is. So the critical value at 5% for one-tailed let's have a look at tables. We're one-tailed, want 5%, and the sample size is 10. So for n equals 10, the actual critical value is equal to 10. So for sample size 10, equals 10, which is greater than 9. So that means we reject H0. There is sufficient evidence, which I'm pleased about, that we've come to that conclusion, because we don't want to be thinking that drinking alcohol has no effects on reaction times. So there is sufficient evidence to suggest that the median reaction time has increased after drinking beer. One pint of beer. All right, so that's it for paired tests. It's the same process as before. We just basically add on the thing D, another row with D in it, and work with the same test as we did before. Okay, so that's it for now. We still have to do another hypothesis test involving Wilcoxon, called the Wilcoxon rank sum test, and then we'll come back to Wilcoxon again, this test again, because we might actually talk about what these values come from, where these values come from, and if we don't, we may do that, but one thing we certainly will do in the final video, the one after next, was talk about how this can be approximated using the normal distribution for numbers which are greater, for sample sizes which are greater than the ones that exist in the tables. Okay, hope you found this useful. Goodbye.